If your head isn't spinning from binary, next we're going to talk about hexadecimal. Hexadecimal is hex, which is 6, and decimal, which is 10, and 6 plus 10 is 16. So this is a base 16 number system, and which means there's 16 digits. And the problem is if we go from 0 to 9, we run out of digits. So what do? Well, let's use letters. So 0 through 9, A through F, 16 digits in hexadecimal. Okay, so let's count in our different bases that we've learned. So we're going to count in binary and base 10 and hexadecimal. So let's start in base 10. We all know how to count in base 10. That's what we're used to. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So notice, when we count from 0 to 9, when we run out of digits at 9, we start over. We go back to 0 and start counting up again. And we just increment our second column from 0, which we didn't write, to 1. Base 16, it's the same thing is going to go on here. I'm going to draw some lines here so that I could keep things lined up. So in base 16, we count from 0 to 9. But we have more digits, so we don't have to stop at 9. We could go to F. But now that I've run out at F, I reset to 0 and increment the next column over. And in binary, when I get to 1, I've run out of digits, so I do the same thing. Increment the next column over. I run out again. Increment the next column over. In all these number systems, you could assume there is a preceding 0 because it has no weight. So I'm just going to fill in all these zeros into the binary. And we usually write binary with preceding zeros to help line up our columns. But I want to point out something here, that in binary, the first column repeats every 2. Probably better to think of it as every 1, it's alternating because it's the ones column. So every 1 number, it alternates. And the next column, every 2 numbers, it alternates because it's the 2's column. And the next column, every 4 numbers, it alternates. And the last column, every 8, it alternates. The pattern repeats every 2 in the first column, every 4 in the second column, every 8 in the third column, and every 8 in the 16th column. But it alternates every 1 in the first column, every 2 in the second column, every 4 in the third column, and every 8 in the fourth column. And these are just the powers of 2 showing up. So we've already seen how to convert from binary to decimal, but now we need to convert from decimal to binary. So I want to convert the number 123 base 10 to binary base 2. The way we do this is we take 123 and divide it by 2. This is 61, and it has a remainder of 1. Then we divide 61 by 2, and 61 divided by 2 is 30 with a remainder of 1. Then we divide 30 by 2. 30 divided by 2 is 15 with a remainder of 0. Then we divide 15 by 2. 15 divided by 2 is 7 with a remainder of 1. Then we divide 7 by 2. 7 divided by 2 is 3 with a remainder of 1. And we divide 3 by 2. 3 divided by 2 is 1 with a remainder of 1. And then 2 divided by 2 is 0 with a remainder of 1. If you read the remainders down and you rewrite it from left to right, this is the binary number. So 123 in binary is 1111011. Now we're going to test this by converting this binary number back to base 10. So I'm going to write out the first 8 powers of 2, and I'm going to prepend that binary number with a 0, so I have 2 nibbles, and I'm going to rewrite the binary number here with the weighted columns above. Any place I have a 1, I need to add those ones up. So 64 plus 32 plus 16 plus 8 plus 2 plus 1. And I don't need any place there's a 0. 0 times 128 is 0. 0 times 4 is 0. So I'm going to get rid of those. And then I'm going to add these together. 64 plus 32 is 96. 16 plus 8 is 24. 2 plus 1 is 3. 96 plus 24 is 120. 120 plus 3 is 123. And 123 is our original number. It's hard to see. That's better. So we went from decimal to binary back to decimal. Okay, now we want to convert from hexadecimal to binary and binary to hexadecimal. Now this actually is a lot easier to do because there's no division involved, but it requires some memorization. So first, we need to write down all our base 16 numbers, and then we're going to write down the binary equivalent for each base 16 number. Remember, we go from 0 to 9, A through F, that first 16 base 16 numbers. I'm going to draw a line every 4 numbers here, so it makes it easier just to keep these lined up. And so binary 0 is 0, 0, 0, 0. Remember, the first column alternates every 1 bit, the second column alternates every 2 bits, the third column alternates every 4 bits, and the fourth column alternates every 8 bits. So now I have a key that gives me a binary equivalent for each base 16 number. And if I have a binary number like 0, 1, 1, 1, 1, 0, 1, 1, this is really two 4-bit binary numbers. And I could just look up the binary number on the table and find the hexadecimal equivalent. So the binary number 0, 1, 1, 1, 1, 0, 1, 1 is the hexadecimal number 7B. And now I'm going to go the other way. I'm going to start with 5A base 16. I'm going to look up 5, which is 0, 1, 0, 1. Then I'm going to look up A, which is 1, 0, 1, 0. And now we've converted the binary or the hexadecimal number 5A to the binary number 01011010. So now I'm going to do base 16 FF, which is easy. It's just a bunch of ones. And we'll start with a binary number now, 10000001, which is 81 base 16. Now 11000011, which is C3, base 16. 1001, 0110, which is 96, base 16. And you can see, if you memorize the pattern of base 16 number to base 2, it's very easy to do the conversion in either direction.